points that yesterday I didn't make them clear. Can you hear my voice when I'm speaking now?
Yes.
All right. So let's just begin. So we are going to do some few definitions. The definitions, they are just very straightforward. If you listen attentively, you won't forget them. So the first thing that yesterday I have mentioned few things that I feel like I didn't give you I didn't give you a good definitions. We talked about the vertex, not vertex, vertex or vertex, vertices, and we also talked, let me just use vertex, and we talked about also the edge, and we talk about the degree. Then after that, we take a step further to isomorphic. Or isomorphism. Then now I want to give you a proper definition that you won't forget when you are working out with any question based on this chapter, because the graph theory, here we are still busy with a graph theory. So when we are still busy with a graph theory. So now, if you have a graph, we have two types of graphs. The first graph that we have, I'm going to talk about, we have an indirect graph. To me, to see if a big screen. We have undirected graph. And we also have direct graph. So those two graphs and the direct graph. So the undirected graph, it's a graph whereby if I draw a graph, I will draw a square, maybe with a triangle. If I draw this graph here, let's say it have a triangle here. It can be A, B, C, D, and E. Then in a direct graph here, I can draw the same graph, but in this one, the direct graph, it will have an arrows pointing, showing the direction of these arrows. So it can still be A, B, C, and D, and E. But the difference between these two graphs is that the other one is going to have arrows. The other graph is going to have an arrows.
Hello?
So, can you hear me?
Yes, did you cut off just now?
I like you. Oh, you can't see.
I can't see the screen.
Oh, okay. Sorry. Can you see the screen now?
Yes.
All right. Let me check if it's also recording. Yeah, it's recording. Okay, let's continue. So this is a direct graph, and the other one is undirected graph. So the undirected graphs, they are the graphs whereby they have it will have an arrows. You'll find it have an arrow in this line here. The arrow may be also here, and then maybe the arrow this way, and also maybe an arrow here, and then also the arrow this side, and the arrow another one this side. So this is a directed graph. So undirected graph, it does not have an arrow at all. Let me just give me 1 minute. Just want to see if I wanted to change like it to see in a big screen. So now, okay, it's fine as long as you can see properly. So now when we talk about the edges of a graph, or when we talk about the vertex of a graph. So the vertex of a graph, we talk about this dot here, 1, 2, the one that I'm cycling, 3, 4, and 5. So if we check this graph, it have 5 vertex. The vertex are equals to 1, 2, 3, 4, 5. They are 5. So when the vertex are 5, you have a line. So when we count this way, in this vertex, in A, if we count in A, we have a vertex called A. The vertex of this graph, if you can write them, is A, B, C, D, and E. So if we count in A, the vertex, if we have a vertex A. So a vertex A, when we talk about, now we are talking about a degree. Let's say degree. So you will see that in A, this vertex is composed of 2 lines, 1 and 2. So the degree of a vertex A is 2. If we go to B, you will see also that the degree of vertex in B is what is 2 also. And if we go to C, when we go to C, you will also see that the degree of a vertex C, the lines that is composed in C is 1, 2, and 3 is 3. And if we go to D, the degree of the vertex D is also 3, is 1, 2, 3. But when we go to E, the E is this one here. The degree of a vertex in E is only 2. So now we have done that. We have done this one to show you how you calculate the degree. You know now how to calculate, how to get the vertex and how to get a degree in each of the vertex. So now when we have done that, we can go to the direct graph. So this is just a sample or example of a direct graph. A direct graph, it have an arrows, but when we have in a direct graph, I will just write, let me write here. I still have it. I'll write it here, direct. I already write that, direct. In a direct graph, so in a direct, if we take A, we have 2 types of a degree. We have inner, we can call it inner, and outer, in degree and out degree. So when we have in degree and out degree, not inner, let's use in degree and out degree. So you will see that here in this vertex A, the outer degree, degree is going out, when the arrow is pointing this way, it means that it's going out of vertex A. So the two outer, we have two, I will just say outer degree of what? We have two outer degree at A. But when we check in B, at this point B here, we have the one inner degree. We have in, which is coming into B, which is 1. And we have also outer, which is going out, which is 1, which is outer, which is also 1, is 1 degree. So, but in combination, if we can add the two, they're going to give us 2 degree. And when we go to C, in C, you will see that there is one which is coming in, and the other one also here is coming in, and the other one is coming in. So we only have inner degree at C, which are 3. And if we go to D, you will see that the one is coming in and the 2, they are coming out. So if you go to E, you will see that one is coming in and the other one is coming out. So we have one inner degree and the outer degree, which is 1 for E. So those how you calculate for a degree in a graph. So sometimes you might find a graph with just a dot like this. So in this graph here, when it's just a dot, it does not have a degree because there is no line within them. So the degree in this, if we can call this n, the degree of n is going to be equals to 0, is 0, because there is nothing there. So now if we can go a little bit further, we talked now about you are able now to get a vertex and you're able to get a degree for all the vertex. So now when you're able to get a degree for all the vertex, yesterday we have a problem of counting an edge, because when we count an edge, for this one to count an edge, we can count it is very simple, but sometimes you can get a graph whereby the graph can be a very, very complicated graph, whereby you find that in order to calculate all this joint line is not easier for us to do it. So we can come up with a way of how can we calculate the edge of the graph. So to a simpler one, it's easier to count because this is edge 1, edge 2, edge 3, edge 4, edge 5, edge 6. So it have 6 edges. So now we have a theorem which helps us to find the edge in a simpler way. So the theorem it states as follows. So the theorem states as follows: the sum of the degree, the sum of the degree of all vertex in an indirect graph with m a degree, then the edges is 2m. So the edges is 2m. So now we know, okay, that if we take the sum of all degree, the edges of this degree are going to be 2m. Edges is 2m. If the sum of this degree is m, then which means we multiply m by 2 to get the edges. So if we take, if we check here in our graph, the sum here of these edges is 2 plus 2 is 4 plus 3 is 7 plus 3 is 10 plus 2 is 12. We get that the sum in this one, it says the degree, the sum of degree which mathematically we can just use as a sum. We can just write it as a sum in sigma notation of degree, which is, we can just say degree, is equals to what? Equals to 12. So when it's equals to 12, for me, in order for you to get the edges, the edges of this is going to be 12 divided by 2, because it's edges is 2m. So in order for you to get the edges, you say 2, you divide this by 2. Then when we divide this by 2, we're going to get 6. So when we get 6, then we know that here in this graph, there are 6 edges. So if we check 1, 2, 3, 4, 5, 6, there are 6 edges. So that's how you do it when you want to find an edges of a complicated or a very big structure. So sometimes maybe you might ask yourself, why are you doing this module? Like, especially this is the part of abstract algebra, even though to you guys is district mathematics. So this graph theory that you are studying now, if you are studying computer science, you are going to have, maybe if you are working in a networking. So if you will be working in a networking, for example, I'll give you example of in a company. You will find that there is one server, or there is one computer for internet cables. In this computer, the internet cable are coming to these devices, going from different computers in the office. So now we can find a relation, we can draw a graph of those internet cable. When we draw a graph of those internet cable, we can now come, maybe you might find that when you draw a graph of this internet cable is in this form. Then you go to another company, you draw the graph of internet cable. So you might find the relation between the two. If the two, they are the same, they are done in the same format. So this is how mathematically this can help you. But this graph theory, it goes further more than that. You can be working in a social media whereby you want to find the relation among the people, the group of people who are subscribing, people who are just like viewing, and people who are maybe becoming a member. So the graph, it won't be really easy. You'll find that the relation, it will be something else, gonna be different in a very different way. So now it's a very interesting module. So now in this one, we have talked about the direct and indirect graphs, but you can have a graph with a loop. The same graph that we are still discussing, it can have a loop. When we say it can have a loop, let's say here is A, B, the same way, C, D, and E. So you find that in this graph here, there is a loop. So in this group loop now, if we have to calculate the degree of A, the degree of A is no longer going to be 2. So when we calculate the degree of A, you're going to find that is 1 and 2 already. But this loop goes this way and it turns again. So when it goes this way and turns, we calculate as from here at the upper, or in the midpoint, not midpoint, in turning point, we could say it's 1 degree plus another one is 1. So the total number of the degree in A is going to be 4. So sometimes when it's 4, so That's how we calculate when we are calculating a loop. So I'm just gonna give you I'm gonna draw a structure with a loop, whereby it's gonna be more convenient for you to understand.
Can we do exam questions like this?
Yes, we're gonna do that. We are almost done with this theory. Okay, we're gonna do that. Let's just finish with this one. Is A, B, C, D, and C. So if you check here in this graph here, we have A here. So if we get the degree of A, so the degree of A is going to be equals to 1. But if we go to B to get a degree of B, the degree of B is going to be 1, which is this one here. 2, 3, and 4 is going to be 4. And if we go to C, to degree of C, here there will be, let's put a loop also. So when we go to a degree of C, a degree of C is going to have 1, 2, 3 is going to be 3. And the degree of D is going to be 1, it's just 1 here. And the degree of E is going to be 1, 2, 3, 4, and 5. So it's going to be 5. So that's how you calculate a degree with the with when it's combined with a loop. So this one which we are discussing today here, we are discussing 1.3, which is about edge counting. So now, if you have a structure with an n vertices or vertice, then in order for you to find the sum of degree, let me just use maths notations. The sum of degree is equals to n minus 1. So when you want to find the sum, when you want to find the edges, this is going to be equals to n. This is their formula that you can use. N minus 1 divide by what? Divide by 2. So if we go to, maybe let's randomly check some question paper. Okay, before we even talk, there is something that I forgot to tell you. Let me just also include it before we talk about the question paper. The notation. So now, if you have seen how I wrote everything that I was writing here, I was using a word notation, which is fine. But as this module is a maths module, so you will find someone when you are writing your answers, they won't be the same. You might be using the word. Someone who's more advanced in a, in a, in mathematics, he might use the other in math symbols. So if you have a line, let's say this is a line, it have a symbol A here, B, and C. Let's say it's A, B, and C. You also have another line here, which is, we discussed this a little bit, but not in detail yesterday, which is X, Y, and Z. Then in these two here, we can call this one a graph G,
We can call this one graph H. So when we say if these two graphs are indeed isomorphic or isomorphic to each other, when we write it mathematically, we're going to say G is isomorphic to H. This is how we write it. So when you see something like this, you must know that this means that G is isomorphic to H. And if I want to prove that in these two graphs, they are isomorphic to H, I will have a Q, like this element, whereby this one, the vertex of G, I can show that the vertex of G, this is how mathematically you can write, is related, is the same as the vertex of what? Of H. And this means that when you write this, yesterday I gave you a proof, I gave you a definition of what is isomorphic. Isomorphic, we said if there is two graphs and these two graphs have the same vertex and edges, then and the subgraph and it have a subgraph, then it means that it is isomorphic. So in isomorphic, mathematically, when we convert it, when we write it mathematically, to prove that these two graphs, they're isomorphic, you are going to prove that V of G, which is vertex, is similar. They correspond with the vertex of H. And when we do that, we also prove that in these two graphs, so you are going to have an injective, whereby injective and surjective. And when these two are injective and surjective, it implies that this graph is bijective. And when the graph is bijective, it implies that is 1 to 1, which I told about yesterday, is 1 to 1. When a graph is 1 to 1, it means that if I have A and B as a vertex, it's going to be mapping to X and Y. There will be a 1 to 1 correspondence between the first graph and between G and H. So that's what happens. So when you have proven that this is surjective, so in the graph, when we draw a graph, you will see as here in this one here, I have Y. In this Y here, we have two chords. The vertex, sometimes when we talk about vertex, remember, if you see the word node is the same. Sometimes we use the word node is the same. So it's the same as vertex. So these two graph here, it have two line being extended edges. So if it have this one and this one here, it means that here, this line, we can call it as an adjacent. These two lines, they are adjacent to each other. Adjacent. When we say this adjacent, if we check the relationship between the two, when we write it mathematically, I can write it in terms of A, B, and C. And then I say, okay, I will check which one correspond to each other. You can see that if I can pick A can correspond as Z, or it can correspond with X, Z or X. So I can choose that, okay, I can choose it for B and X. And also, if you check B is a vertex whereby is extended with two adjacent, which is A and C. And which one also, we will see that Y here is the only one which is extended by X and Z. So which means B is going to be corresponding with what? With Y. And C we can say is Z. So someone can also write in terms of this way, say A, B and C, Z, Y and X. So you guys, you are in the same WhatsApp group. So if we check also, the other thing that we're gonna check is X and Y. You can see that there is no line here in X and Y. When there is no line, is there any line that is extending or joining A and C? We find that there is no line that is joining A and C. So then we can conclude that, okay, these two graphs, they don't look the same, and you might think it's not the same graph, but we can now say, according to what all things that we have said, this graph is meeting surjective because A is mapping with what? With X, and B is mapping with Y, and C is mapping with what? With Z. And if you check also, we can check A, it have one what? If we check the edges, you will find that is 1, 2. Vertex is 3, is also 3. If you check the degree, you will find that C, it have 1 degree. X is have 1. This one, it have 2. This one also have 2. And C have 1. And Z also have 1. So we can conclude that, okay, G is what? Is isomorphic to H. So mathematically now, just what I just wrote here, which is this one, and this one. This is what I have proved that G is isomorphic. So sometimes you can use words that vertex of H equals to vertex, then you conclude that is 1 to 1. Then after that, you're still going to be doing the same thing, but not in the same notation, right? Not using the same notation. So the other one, which I'm not gonna do it today, there is a proof that you might need to know, but we're gonna see if in your question papers, in the question papers they do ask you. So yesterday we opened one of this question paper for 2018. So in this question paper, yeah, we managed to do question number A, we did it. A, B, we did that. And then also B is fine. Then the other one that we did, I'm not sure if we should repeat it, is C, number 2. But I think it was more clear to you, this one. I'm not sure if you can have a comment.
I didn't understand the last question we did yesterday.
The last one, is it number 2, question 2, this one?
The one after that.
Okay. This one, eh? Oh, this one is the solution, sorry. You mean this one, number C?
Yes, I think so. C.
Okay. So let's look at C. The first thing that you're gonna see here in C, we will understand the first thing that is going to come to us is that this is a direct. It's a direct what? It's a direct graph. It's a direct graph. I haven't read the question. So what does the question says in C? The question here, the first, okay, for each of the following pairs of graphs and direct graphs, determine whether they are isomorphic or not. If they are, give a vertex correspondence. If they are not, give a reason why. So number C, yes, there it is. So the first thing that we're going to check, we can first check what the vertex of this graph. So if we check here, we have 1, 2, 3, 4, 5, 6. We have 6 vertex. When we have 6 vertices, we check here, we have 1, 2, 3, 4, 5, 6. We also have 6 vertices in this one. I will just use V. Now, when we have 6 vertices, it means that indeed in both graphs, the degree, how many degree, we can check the sum of a degree. So if we take A, you will see that A, it have a degree. When you write, you can show everything when you are writing, when you are answering this question. You will see that the degree of A, let's say degree of A, I'll just write only A. The degree of A, you will see that is 1, 2, 3, is 3. When the degree of A is 3, and we check is 1, 2, 3, even for B is 1, for B is 1, 2, 3, 1, 2, 3, 1, 2, 3, everything is 1, 2, 3, is a 3 degree. So we check also the degree of C. A, this one, the first degree is 1, 2, 3. But the problem part is that here in the direct, we are given the arrows showing, pointing on the in. I talked to you about the out and the in. So if we check here, in number 1, we have 2 in degree, is 2 in degree. We also, which means, and then the 1 is out. Outer is 1 in number 1, in the vertex 1. So, but in vertex A, we have 1 in, and let's check 2 in, 2 out. So if we check, we can say, we can check the one with 1 in and 2 out. So if you see here in number 4, we have 1 in and 2 out. You see that. So we can say A is related to, is in relation with 4, this one here. And if you check also, let's go to number, let's check the one with we can find with 1, 2 in and 1 out. If we check B is 1 in and 2 out. You see that we can say B is related to 1. And let's check C is 2 in and 1 out. So also C, it can be related to 1, and also C, it can be related to, let's check if here is number is 2 in, 4, it can also be related to 1. Okay, 1, 2 in. Okay, number C is 2 in and 1 out. 2 in and 1 out, and 4 is 2, 1 in and 1 out. Okay, let's check 3. So we can say 3 is C is related to 3, is 2 in and 1 out. It's related to 3. Then let's go to D. D, here you will see that 2 graphs here. The 2 one they are in and the other one is out. So we already have 1, 3, 4. Let's check 2. 2 is 1 in and 2 out. And then we already did number 3 is 2 in. We already have this one. Let's check 4. 5. 5, if you check, is 2 in and 1 out. So number D is 2 in and 1 out. We can relate it with number 5. And number E, we can relate it with, it's 1 in and 2 out. So let's check C, number 6. 6 is 1 in, 2 out. You can see that. And then E is 1 in and 2 out. We can relate with this E with 6. And then F, the only one we left with here, I think, is 2. F is 2 in and 1 out. 2 is 2 in. It can relate with 2. So there is this relationship that we have shown that, okay, they are related. But if you have seen, here in this graph, we could see that this graph here, when we have to check isomorphic, we have to check about the vertex is fine. But when it's mapping 1-to-1 function, it means that there must not be any function if I have A and B and C, D and E. There must be, let's say it's 1, 2. This one, I'm just giving you an example. If one function, it can map from one and another like this, is this function is not 1-to-1. So if it's not 1-to-1, then we can check in these two here. In these two function, you will see that here, in these two function, there is a two function. When I was doing it, if you check, there is a 2 functions which map from one to another. They were mapping between the 2, but that one, it may not really give us a full conclusion. So we can leave that part then. But now let's go back. We check something. We check something. You will see that if I draw in this adjacent here, if I draw 1, 4, if I draw 1, 2, 4, if I draw 1, 2, 4, let me draw it like this way here. You will see that 1, 2, and 4, 1, 4, and 2, they are what? They are joined. But if we get here, we draw something here, let's check. I started at 1, 2, 4. If we check here also, you will see that if I start at A, which is this one here, I'm gonna go with it. I go this way. I also go this way. It's end there. You can see that this graph is not joined. A, D, which is this way, and F is not joined. It's just this way. So because this one is joined and this one is not joined, this is, we call it a subgraphs. The subgraph of them, they are not the same. So when the subgraph are not the same, this one, when we talk about the subgraph, we were talking about that. I gave you an example of injective. In the injective, we talk about they all have the same adjacent lines, ne? The adjacent line connected with the same adjacent. But when we come to check the surjective is not equal. So this is what we have proven here when I talk about the subgraph, the surjective. But now they are not the same. So because of this here, this reason, so we can state that these two graphs are not what? They are not isomorphic. So that's how I have given you how. So everything that I've been writing, the way I've write here, is what you can also write while you are checking if something is isomorphic or not. So if we check it, they are not isomorphic since the subgraphs, you see what I've said, the subgraphs induced by the vertex within degree 2 and out degree, there is in degree 2 and out degree of what 1 are not isomorphic. So they are not isomorphic. So when they are not isomorphic, there they draw it for you, one of the graph and the other one, they use different. You can use also different to prove that. Then the first subgraph is connected while the second one is not connected. So that's how you checked it. So if now, how you can come up, sometimes you can say, we can see that if we start at A, I'm just giving an example. Let me erase here. The way here they answered, you will never answer like a memo. Unless that's if you know the question is exactly the same. But if the question comes and is more different, but you use the same strategy, you won't answer it exactly the way. But the answer, if you are following the instructions, is gonna be exactly the right answer, even though it will be different. So let's look at A. If we look at A, you will see that here in A we say is related to 4. You see this for here. If we check 4, if I go, there is incoming and 2 outcoming. So if you check here, if in A there is 1 incoming and what, and also 2 coming, you will see that is A. I can write this dot, and dot like that. The other one is incoming. The other one is outcoming. This one is outcoming, incoming, and outcoming. And the other one also it's outcoming. The other one there is outcoming. But those ones, they are not really important. We check at 4. If you check at 4, its incoming is fine. It's outcoming there, but they joined. So that's the problem. That's where you must show. So if we analyze, let's check in their example here. This one they give, they showed with C. Let's check where C is. C is there. Then they go to C. If you extend it, you will see that when you go, it go to D, and it's also gonna go to F. So I showed you with A, F is different. It's the same thing. So 2 are incoming and 1 is out. 2 are in, 1 is coming and the other one is out. But when we go to 1, if in C, my C is related to 3, you will see that there is 3 also here. When we go to 1, number 1 here, where is 1? Or we can go to 1. Okay, yeah, there it is. We have 1. Let me check. 1 is there. So when you see 1 here, 1 is going to go to 4. 1 is gonna go. It's incoming. Okay, I can't see. Let me erase here so that we can see properly. So if we check here in number 1 or in number 1 here, you will see that the other one is going out, the other one is coming, but the other one there is coming in also. So when it goes, we gonna, even if we take, let's say is 5, number 1 cannot be, okay, we have 5 also. 5, it have 2 incoming and 1 outcoming. But if you take 5, 5 is related to D in my mind here. But if you take also 5, you will see as an example, 5 it have 2 incoming and 1 incoming, and C here it have 2 incoming and 1 going out. So we can also give an example. You can also use 5. So if you start at 5, when you draw 5, it's going to be this dot. Incoming is going to go down there. It's gonna be like it's 5 here. Incoming is gonna go down, and also the outcoming incoming is 1, outcoming is 1. Then the other one is incoming is what is 2. So this one here, the way they've drawn this dot, I think they just showed with different, because if you start at 1, if you start at 1 here, it's still the same as you have started at C. And even if you start at 5, because they have two incoming. So, but there are those 2 incoming, this point, they have 2 things that incoming and 1 out. So, but they are not connected. So that's what they show. But even if you show the way I have done with you now, it's a proof that these 2 graphs, they are not related. They are not isomorphic. So I don't know if like it's very clear to you.
I think I understand.
All right. Yes. So the only thing that you must take into account is that just take 1, check the vertex the way I'm doing with you, then you're gonna come to a right conclusion. So this one here, it says if a graph G has n vertex, all of which but one have odd vertex degree, how many vertex of, okay, let me read. If a graph G has n vertex, all of which but one has odd degree, then how many vertex of odd degrees are there in G, the component of G? So how many degrees, how many vertex of odd degrees are there? So if what we take here, we check the first thing that you're going to put, you have to know what are you talking about. We need to know about the odd degrees. And we are talking, in other words, we are talking about the degree. How do you know, can you find a degree of n? A degree of n is n minus 1. So which means n, if is an even, which means it's going to have n minus 1 as an odd degree. So when it's going to have n minus 1 as an odd degree, so the question says, how many vertex of n degrees are there in G? So it's n minus 1. That's all. You don't need to, I already gave you the formulas, so you don't need to reason too much. You must know that is n minus 1. So if you check here in your solution, I'm checking now, you'll see that if all, here they are just explaining, this is just an explanation. If all but one of the n vertex of G is odd, it means that G has n minus 1 vertex of odd degree. But then by the correlation of theorem, what this is just they are telling you n minus 1 has to be even, and therefore n is odd. Ne? Then they will tell you if a G has and what their n degree, they are just telling you there is odd exactly when D is what you can read this. So but the answer here, it have to be n minus 1 vertex. They are n minus 1. There is nothing much that you need to understand. So you only have to remember the formula that I gave you previously in this video, that if you have n degree, how many degrees are we going to have? So do you have any question with that, with this one? I don't want to read it further, but you can go, or you can read it and understand more, but
No.
you understand, right? Yes. So you just have to know that to calculate the degree is what is this one. This one here is even, this one is odd. That's all. So the others, okay, this one we won't do to it today. We haven't started with this one. We have to first do it, the circuit one. So we will do it when we have, even the others here, we'll do it when we have started. Let me check. These ones, yeah, going forward, we don't have. Maybe we can find another question paper. We can find another question paper. But I think so far, according to my understanding now, I think maybe so far what we did with MAT3707, you are getting the, it's very simple. It's just a beginning. So I think you are not having a problem, unless otherwise if you having any problem that you can tell me. And do you have a book for this module?
Yes.
All right. So this one, the problem I think is for 2012, but I don't like using question paper for old versions. But let's try to do it. No, we have done this one. Yeah, we did this one. It's the first one that we used. So can we get more question papers?
I sent you the 2022 paper, but there's no memo.
Oh, okay, no problem. So this is the question paper for 2022. Let's check it out. Okay, this question, I'm not going to repeat it. This one. The first question, I'm not going to repeat because we already did this one. Okay, but this one I'm going to show you now. It's fine, but we already did it. It's the same one, but I'm going to do question number 1. But question number 2 is exactly the same as that one for 2018. You can see that. Maybe let's just do it, but it's the same. You just copy what we did there. We're even doing it now. The one that you said, determine whether the following 2 graphs are isomorphic. Fully justify your answer. Okay, let G be a graph with n. Okay, that one is another question. So now if we have to determine these 2 graphs, if they're isomorphic, you first check the vertex. Is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. You can see the vertex are the same. We have 8 vertex. Both have 8 vertex. And then second thing, we check the degree. You can see in this one is 1, 2, 3. In this one here, A is 1, 2, 3. 1, 2, 3. So even here, this is, I talk to you now about the loop. The loop you count as 1, 2. So if we go to 1, you'll see it's 1, 2, 3. So they both have 3 degree. Then we go to, after that, we check the subgroup. Let's check the subgroup. When we check the subgroup, if you start at A here, you will see that A is gonna go from here. You write a line, you draw another line. You see that. But if we can just take 1 here, let's assume that you are taking here 1 here. If we take 1 A, 1 is going to be like this way, but there is loop. You see, it's gonna be this way. Okay, not the way I've drawn. I didn't draw it properly. Let me draw this one from A. From A to is going to be, this is A, is like this way. This is A, H, and E. Then if I take here from 1, if I'm saying, okay, A is related to 1 because this is just a cycle, it's going to be A is going to be 1. You go straight until you get here. Then after that, you can see that we have 1 going this way until 6. But here there is a loop. It get looped. So this is not looped. It's not the same. The subgroup is not, they are not the same. So now you can conclude that because of the subgroup, this is not isomorphic. It's not isomorphic. They are not isomorphic. So did you see what I did? no matter which point you take here, né? Or you start at 4, you will see that when you go there, you see it's also it have a loop, everything, so it cannot be the same as this one. They will never be the same. So these are isomorphic. You show that they have same vertex, but the subgroup fails. So it's isomorphic. If you go back to that question we were doing, if I can't, we did something like this in one of the question. I can't remember if I think it's in that paper. There was a question there. I want to show. Yeah, there is a question we did similar exactly, unless that's if I just saw it somewhere alone. But yes, you see this one here, this graph here. Okay. Yeah. Number A, for which we have A, B, C, D, A, B, C, D. So in this one here, we found that these two, they are more. If we check, let's check with here. If you check, it have 1, 2, 3, and then it also have 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. It also have, if you check A, it's going to be 1, is 1 only. Okay, let me check something. In this one here, the solution, the two graphs are isomorphic. One vertex correspond is given by A, is corresponding to 1. If A is corresponding to 1, is 1, 1, 2, 3, is fine. B is corresponding to 2, is okay, B is 3, and then C is 5, and so on. But if we check this drawing here with this one, is not, they are not really the same. They look the same, but if you check properly in this one here, is 1, 2, 3, and then after that when it gets extended with 4, these two, they are not. This one is 1, 2, 3. That one is 8. So the moment when they put, it's making this one, that one not to be. It can't be the same. So here, if we let's check about the subgroups. If we check a subgroup of here, if we start at A, then A is related to 1. Okay, this one it can, because 1 to 4 there is giving us a loop. And then A1. So, yeah. So if you check something, why are they related? So if you start at A here, let's start at A. So in A, you're going to go this way and this way. It's going to be like this way. So when we start, because the adjacent here is this one and this one. So this adjacent, if one is related to this one, this is the same as the adjacent, the two loops. So when we take from one here, we're going to say one like this way. It's going to be like a loop, this one and this one, the adjacent. We take the adjacent. So you can see that both here, there is nothing. So that's why this one is related. So let's go to us here, the one we're doing. This one here, we found that for this one, let's redo it, the question. We found that, if this one here, we're starting at A, both they have same, but if we're starting at A, in our A, we have A here is going to go to F this way, which there is nothing. So if we are saying A is similar to this one, then the vertex of A, 1, 2, is going to be this one and this one. Yeah, sorry, I was wrong there when I extended there. So which means the vertex is going to be like this way. So even in 1 there, it's going to be, it won't loop from, we don't extend it that way. We extend it based on the adjacent. So it's going to be the same. So yeah, so this also is also what is also an isomorphic. is also isomorphic. The first thing, when we talk about the, maybe there's something that I will say now so that you don't remember, so that you remember. When we talk about the subgroup, that I think I didn't give you the proper definition of a subgroup. In a subgroup, when we check if I'm taking A and A is related to 1, it means that in A here, we will find that it's extended. Our A is extended by what? 1, 2, and 3. Ne? 3. There is something 1, 2, and 3. And if we check here also in our A, you can see that A is also extended by 1, 2, 3. Ne? Then when it's extended by 1, 2, 3, if we take A here, you will see that when you draw from A, you can draw something like this way. Let me start with A there. You can draw, we already draw it, is this one and this one. But also there is a middle one. Even if I don't really draw the middle one, I can draw something like this, and this. But it's not, there is nothing that if after that, if I extend up to here, the line is joining. So even in A here, you will see that if I can draw number 1 here. I can draw this one as way, this one is a loop, but there is also this line here going down to 6, but it's not joining the same way as this one. So we mean these two things here, we can see that they are the same. So that's why we will conclude that this two graph is what is isomorphic, because this one in the middle, you don't really have to take it into account. We can leave it. So it's isomorphic. Any question?
No.
Okay. So the other one, is it possible to have a connected polar planar? Or this one, we haven't done this one. So the second one says draw two non-isomorphic with degree sequence of 0, 1, 1, 2, 2. So to draw that, yesterday I showed you can have this one here. You can start with this one here. You can have 1, 1, 1, 1, 1 is 1, 2, 2. Yeah. Then with another one here, the 0, 1. Or you can have, this is the first one. They say two non-automatic none. So you can also have 1, 1, 1, which is like this way. And also the 2, you can write 1, 2, 3, not connected. Yeah. So those are two those are two non-isomorphic graphs. So okay, thank you. I see another question paper there. Maybe let's touch it. Let's touch the other one there. Let G be a vertex. Okay. Let me just open it. I want to check. Okay, this is the memo of 2015. I don't have a question paper there. I think you sent only the memo. Okay, let G be a graph with vertex G and edge. Okay, define the component of G bar of, okay. Okay, for this one, I think maybe our next class, we're gonna also do, in our next class, we're gonna also do this one for 2015.
Okay.
Yes. So because today is holiday, maybe we can cut this time. Then we also have a class tomorrow, unless otherwise if you are saying you're gonna be busy with something, but we can have a class tomorrow also. So are you gonna be busy tomorrow or is it fine?
No, I'm not busy, but okay, we can have a class tomorrow.
Tomorrow, yes, because as it is weekend, so I'm trying to cover those other days that we didn't have a class through this.
5 o'clock. 5
No,
p.m.
hello? 5 p.m. Anytime when during Saturday and Sunday, actually I don't teach. So, but for you, because we didn't cover the classes. We remember we missed many classes before. So I'm trying to push so that we can cover those days. Even today, normally on holidays I don't teach, but I decided that I must teach. We must have class because we didn't have class for some other days. So I think maybe we can tomorrow. You say 5 p.m. is fine, right?
Yeah,
Then
that's fine.
all right, no problem. Then I will see you tomorrow. Maybe you can be checking what we did. So the other thing that I